Piping vibration, Thermowell corrective actions, effective solutions for improving thermowell performance. This topic refers to guidelines for the avoidance of vibration-induced fatigue failure in process pipework by Energy Institute. Introduction to Thermowell corrective actions. Thermowells are critical components in process systems, designed to protect temperature sensors from harsh operating conditions. When a thermowell exhibits a likelihood of failure, LOF, equal to 1, corrective actions become essential to ensure operational safety and reliability. This presentation focuses on design solutions, best practices, and remedial measures outlined in Technical Module T12. The primary goal is to mitigate risks associated with vortex-induced vibrations and structural failures. Redesign or replacement of thermowell, reduction in fluid velocity. One of the most effective corrective actions is to redesign or replace the thermowell with a model that has a higher fundamental structural natural frequency. This adjustment ensures compliance with TM04 criteria and minimizes the risk of resonance caused by vortex shedding. Redesign strategies may involve altering dimensions, material selection, or mounting configurations to enhance stiffness and reduce susceptibility to dynamic forces. Replacement should be considered when the existing thermowell cannot meet operational requirements or when modifications are impractical. Engineers must evaluate process conditions, such as fluid velocity, temperature, and pressure, to select an appropriate design. The goal is to achieve a robust thermowell that withstands operational stresses while maintaining accurate temperature measurement capabilities. Reducing fluid velocity is another practical approach to mitigating thermowell vibration issues. Vortex shedding frequency is directly proportional to fluid flow velocity, therefore, lowering the velocity can prevent lock-on between vortex shedding and the thermowell's natural frequency. This adjustment may involve process optimization, such as throttling valves, modifying pump speeds, or redesigning piping layouts. While effective, this method requires careful consideration of process performance and efficiency, as reducing velocity could impact throughput and system functionality. Engineers must balance vibration control with operational requirements to ensure that corrective measures do not compromise overall plant performance. Finite element modeling, dynamic strain and vibration measurements. Finite element modeling, FEM, offers a sophisticated approach to predicting thermowell behavior under dynamic conditions. Unlike simplified calculations, FEM provides accurate estimations of natural frequencies and dynamic stress levels, enabling engineers to identify potential failure points before they occur. This method involves creating a detailed computational model of the thermowell and simulating operational conditions, including fluid forces and thermal effects. By analyzing stress distribution and vibration modes, engineers can optimize design parameters and validate corrective actions. FEM is particularly valuable for complex systems where traditional methods may not capture all influencing factors. Implementing FEM requires specialized software and expertise, but its benefits in enhancing reliability and safety justify the investment. Dynamic strain measurements using bonded strain gauges provide real-time insights into thermowell performance under operational conditions. These gauges detect strain fluctuations caused by vibration, helping engineers assess the severity of dynamic loading. However, installation during operation is challenging and typically requires specialized skills and equipment. Another advanced technique involves measuring vibration velocity at the thermowell tip through its internal bore, provided the bore diameter and temperature allow. This method helps confirm whether vortex shedding is exciting the thermowell as fluid velocity increases. Both techniques are diagnostic tools that support decision-making for corrective actions, ensuring that interventions are based on accurate, empirical data rather than assumptions. Velocity collars and welded gussets. Structural reinforcement can enhance thermowell stability, but its application requires caution. Velocity collars aim to reduce the unsupported length of the thermowell, theoretically increasing its natural frequency. However, achieving sufficient contact between the collar and the pipe wall is difficult, and improper installation may reduce the natural frequency due to added mass. Therefore, velocity collars should not be the primary corrective measure. A more reliable solution involves using 4-way welded gusset plates on thin-walled pipework. These gussets increase stiffness at the Thermowell connection point, significantly raising the natural frequency and reducing vibration risk. The effect of gussets can be predicted using the wall thickness modifier FM. Proper design and installation of gussets requires skilled fabrication and adherence to engineering standards to ensure effectiveness and safety.